Hello, everyone, and welcome to the first day of online learning. This is Mr. Starita coming at you from New Jersey, my parents' home. This is where I am during the quarantine. But nonetheless, physics persists, and we will be doing these online lectures for a while. So we will be learning about momentum in this unit. We are starting a new unit. And to follow along with this lecture, make sure you go to Google Classroom and you either print out or have available the notes for this lecture. It's just impulse momentum theorem lecture notes, and there will be opportunities for me to for you to pause the video, do out some problems, and take notes along the way. So let's delve right in to momentum. Well, what is momentum? The everyday use of the word, right? You guys have heard this term before, and it's a lot of times used in a sports context. So I have this analogy right here saying, going into the 7th game of the World Series, the Chicago Cubs have the momentum they need to win this game. So what does it mean if a team has momentum? Well, it means that they're on the move and they're going to be hard to stop or something like that. So when we talk about momentum in a physics context, what is momentum? Well, it is the quantity of motion for a moving body. The quantity of motion for a moving body, that's kind of a vague term. So let's think about it the way that Isaac Newton might have thought about it. Well, you're standing at the bottom of the hill. That's you. You are the stick figure. And at the top of the hill, there is a soccer ball and a boulder. So when each object hits you, which one do you think is going to have a higher quantity of motion? So think about it for a second. So if you thought that the mass was an important feature of this quantity of motion, you might have said that the boulder has a higher quantity of motion. And if you thought that the velocity had a higher, if you thought that the velocity was an important feature to this idea of quantity of motion, then it's kind of hard to say because we don't have any numbers here. We don't know how fast they're moving. But this idea of quantity of motion is actually both of those things. It's how fast the object is moving and how massive that object is. We will get back to that in a little bit later, but for right now, just keep that in the back of your brain. So how do we change an object's motion? Well, in order to change an object's motion, we have to apply a force. So we can apply a force in many different ways, but I have this example here where we have two cars have the same quantity of motion. So they have the same mass and moving at the same speed. They are identical. And we can stop these cars in two different ways. We can either stop it with a brick wall or with a bale of hay. So which car would you rather be in? Think about it for a second. So what's the difference between the forces applied by the wall and applied by the bale of hay? Well, when we crash into the wall, it is over like that. It's over in a split second, as opposed to the bale of hay, which is something, it might have a little bit less impact. So in this idea, right, how we change an object's motion depends on two different things. It depends on the force that's applied to an object, and it is dependent on the time over which that force is applied. Now, in physics, we call that an impulse. What is an impulse in the everyday use of the word? Well, I have this convenience store counter, which you guys have all seen before, the candy at the cash register. What does it mean to act on an impulse? Well, it means you're going to buy the candy on, spur of the moment decision. And, you might not have bought it if it wasn't right there, if it wasn't being advertised to you, if it wasn't, in your face. So this idea, of impulse is, a spur of the moment decision and, this idea of a force of advertising. So in a physics context, an impulse is a force acting over a given time interval. It's the force over which that time, or over the time of which that force is applied. Now we have the impulse momentum theorem, which states that the impulse, the force times the time, is equal to the change in momentum. You guys have seen that delta sign before, that it's the change in momentum. Now we use P to denote momentum because when Isaac Newton was studying this stuff, the quantity of motion in Latin started with a P. So we kept that in English. So momentum P is equal to the mass times the object's velocity. So now is a good time to go to your note sheet and try out an example. If a 2,000 kilogram car is driving 25 meters per second east, what is that? What is the car's momentum? So pause the video, try to do out this problem on your own, and we'll come back. So hopefully you pause the video, and we're going to see how to solve a problem like this. Well, we know that the momentum of an object is equal to the mass times its velocity. And we were given those two quantities, so we multiply them together, and we get an answer of 50,000 kilogram meters per second east. Now the units of momentum are kilogram meters per second. There is no fancy unit for momentum, it's just the units of mass times the units of velocity. And it is important to denote direction when signifying the momentum, because momentum is a vector, right? Momentum is a vector quantity. It means it has a magnitude and a direction. So let's do out a second problem. So what is the momentum of a 12,500 kilogram airplane waiting to take off on the tarmac? So pause the video, try out this example, and we'll reconvene when you're done. So hopefully you pause the video and try this one out, and let's see what the answer is. So we have our same formula, and we have the mass times its velocity. It is waiting to take off, it is not moving. So its momentum is 0 kilogram meters per second. So stationary objects have 0 momentum. That is important. Stationary objects do not have any momentum. Momentum is the quantity of motion for moving bodies. Good. Let's do out one more problem with just momentum. So a bullet fired from a gun travels at 1,300 meters per second. And if it has a momentum of 27 kilogram meters per second, what is the mass of the bullet? So try solving this one out, and we will reconvene when you're done. So let's see what the answer is. We have our formula for momentum, and if we plug in what we know, we can just divide through and find out that the mass is 0.02 kilograms. So using this momentum formula is really not super challenging. It's just a couple quantities, and we can manipulate it in a couple different ways. So let's change gears a little bit, and we are going to find out where Newton's second law comes from. I think this is pretty interesting, and hopefully you guys will too. So we have the impulse momentum theorem, which states that the impulse is equal to the change in momentum. And we know that the momentum is just the mass times the velocity. So if we do that out, this next line, this second line, for those of you in calculus, you may recognize that that is the product rule. For those of you not in calculus, don't worry about it. Just, take it at face value. And that is how we multiply out that delta sign. So we're going to divide through by the time to get the force by itself. And now we have the force is equal to the mass times the change in velocity over the change in time, plus the change in mass over time times the velocity. Now, some of you guys might recognize this term right here. So what do we think that term is? Do you guys remember that term? Well, hopefully we do. And hopefully we recognize that it is the acceleration, right? The acceleration is the velocity over time. It is how the velocity changes over time. So we have F is equal to ma plus this extra thing out here. I'm going to erase this. Oh, excuse me while I navigate the Zoom recording. So we have F is equal to ma plus this extra term out here. So what that extra term is a correction term. And what that's saying is that the net force is equal to the mass times acceleration plus the change in mass over time times its velocity. Now, for something like a car, right, does a car change its mass over time? What do we think? Well, it does, right? So we can have a full tank of gas. That is the tank in which gas is kept, and we can have a full tank of gas. And now if we're driving over a certain amount of time, you know, we might start to lose some gas. So the tank might get empty. But for something like the problems that we're used to with boxes or, you know, balls falling or something like that, the mass doesn't change. And for something, you know, like a car driving a few feet down the road or a few meters down the road, the mass change is pretty negligible. Now, for something like a spaceship, right, we have a spaceship. Oh, that is still the eraser. Let's do, okay, come on. Why is this happening? Okay, so bear with me while I try something else out. Okay, so we have the pointer. So hopefully you see where this red dot is. And that is the actual space shuttle part. That is where our astronauts are. They are right there. Now, everything else below that, everything else below this red dot is just a tanker for fuel. So something like a spaceship is going to have a very big mass change over time. Let's see. Aha, there we go. So there is the red line. Everything below that red line is just a storage for fuel. So you can see that a spaceship is going to have a very big mass correction over time. But for something like the problems that we do, we don't really care about the change in mass over time. So Newton's second law is actually just an approximation of the impulse momentum theorem. And if we think back to what Newton's second law says, that force is the net force. So when we are dealing with the impulse momentum theorem, we are dealing with the net force on an object, just like we would in a Newton's second law problem. So we go back to our original problem of a car hitting into a wall and a pile of hay, but this time we're given some numbers. So we can use the impulse momentum theorem to analyze the system, analyze why it would be worse to hit into a brick wall versus the pile of hay. So we have our impulse momentum theorem, and let's plug in the numbers that we were given. So we learn that our change in momentum is negative 30,000 kilogram meters per second. There is no final velocity, it's stopped. Now, because the change in momentum is the same for these two cars, that means that something has to be different about them. Either the force has to be different or the time has to be different. So for the brick wall, right, the force is larger over a shorter amount of time. So I put in some numbers, right? A brick wall, or when you crash into a brick wall, it's over like that. In a split second, you know, 100th of a second, it's over. So our change in our force that's applied is 3 million newtons. And now the force applied on the hay bale, or the force applied on the car by the hay bale, excuse me, is going to be smaller because it acts over a larger amount of time. Now, why is it more deadly to crash into a brick wall? Well, because the force is just so much larger, right? It happens over a shorter amount of time, and the force has to be larger because the change in momentum is the same for both of these objects. So let's do out some example problems. So the next example problem is a 15 kilogram air jet accelerates from rest to 45 meters per second before it takes off. So what is the change in momentum of the jet? Let's take a second and do this problem out. And hopefully you pause the video, and if we come back to see the answer, well, we know that the change in momentum is going to be the mass times the final velocity minus the mass times its initial velocity. And plugging in what we know, it starts from rest, so its initial velocity is 0. We get that the change in momentum is 675,000 kilogram meters per second. Excuse me. So let's do out another problem. A 2,000 kilogram car is driving 25 meters per second east and stops in 5 seconds. What is the average force stopping the car? Let's pause the video, take some time to try to do this example out, and we'll come back. So let's see, what is the average force stopping this car? Well, we have the impulse momentum theorem, and we know what the change in momentum is equal to, and plugging in the numbers that we know, it stops at the end, so its final velocity is 0, and plugging in the numbers that we know, we get that the force is negative 10,000 newtons. Now, what does it mean to have a negative sign out front? Well, that negative sign comes from the fact that we assign the positive direction to the right. And in order to stop this car, we have to apply a force to the left. So that negative sign tells us that our force has to be applied in the direction opposite this car is moving. All right, let's do out one more example. A 5 kilogram ball is dropped from a height of 30 meters and falls in 2.4 seconds. What is the speed as it hits the ground? All right, so let's come back, and we are given the impulse momentum theorem. All right, let's see how this object's changed. Well, we know that the force applied to this, the only force acting on our ball is the force of gravity. So we can plug in mg for our force and multiply that by the time it takes, and the change in momentum is equal to the change in momentum. So now we plug in the numbers we know, and we are interested in finding the final velocity of this object. We drop the ball, so there is no initial velocity. All right. So if we solve out for the final velocity, we get an answer of 24 meters per second. Now, it's important to know that, I gave you guys the height was 30 meters. That didn't matter in our case, right? It might have mattered if we were using kinematics, but now we're using impulse and momentum. It's also a lot easier than kinematics, right? We only have one formula as opposed to the 4 that we had before. So, makes our lives a little bit easier too. Now, the very last thing for this lesson is the egg drop. So 2 identical raw organic large eggs are dropped from 2 meters above the ground. Egg A lands on a pillow and survives, and egg B lands on the concrete and breaks. So answer the questions on the notes page for egg A is the pillow egg B is the concrete, or C, the 2 are the same. So pause the video, take some time to do out this problem, and we'll come back and explain the answers. So hopefully you paused the video and did out the 5 questions, and I'm going to show the answers now. So hopefully they match up, but if not, let's talk about it. So number 1, which egg has a larger speed after it falls the 2.0 meters? Well, they both have the same speed, right? They're both identical, they both have the same mass, and they're both dropped from the same height. so they should have the same speed as they hit the ground. Which egg experiences the larger change in momentum? Well, they both have the same change in momentum, right? Because they're identical, they both have the same quantity of motion, mass times velocity, and it goes to 0 at the end when they stop moving. So which egg experiences the greater impact force? The egg that hits the concrete, right? It is not, because they have the same change in momentum, either the time or the force has to be different, right? So in the concrete, just like our brick wall, is over in a split second. So the force must be greater. And because of that, for number 4, which egg experiences the greater impact time? Well, the one that hits the pillow is going to have a greater impact time and a less force. And which egg experiences the greater impulse? Well, that's just the same question as 2, right? The impulse is the change in momentum. So if they both experience the same change in momentum, they will both experience the same impulse. So in summary, an impulse is a force acting on an object over a given time interval, and the quantity of momentum is the quantity of motion for a given body given by the mass times the velocity. And the impulse momentum theorem states that the impulse of an object is equal to the change in momentum. So thank you guys for listening into this lecture. I wanted to talk a little bit about the future and what it's going to look like. So you guys have an assignment to do for this lecture. It is in Google Classroom under the same place where you found this video, and that is going to be due on Thursday, March 26th. So you can scan the answers, print it off, scan the answers using a free scanning app, and you can post that directly to Google Classroom. If you don't have a printer, you can write the answers on a separate sheet of paper. And if you have any difficulties submitting the assignment, please email me. So the next lecture on the conservation of momentum is going to be Thursday, March 26th, the same day that the assignment is due. But before that, you can have a Zoom check-in. So we want to meet, both Dr. Bright and I want to check in to make sure that Zoom is working, so that you guys can talk to us if you have any questions. So those check-ins are going to be this Wednesday or Friday. You do not have to come to both, but please come to one of them at 1 p.m. On top of that, I'm going to have daily office hours for 4 hours a day over Zoom, so that we can talk about these things. If we're going through these notes and anything confuses you, or if you're working on the assignment and you have questions, I'll be around to talk. Now, I'm not going to be on the Zoom call the entire time, but I will make myself available for those 4 hours. So in order to talk to me, please email me so that we can talk and set up a time to meet over Zoom. You can email me, you can email Dr. Bright and talk to him as well, because he is also your teacher. But yes, so that is what the next couple days are going to look like. And I will see you guys on Wednesday or Friday, hopefully. All right. Bye, everyone.